Hi there guys, welcome to this video where we're going to take a look at a problem that I've taken from a sixth term examination paper to have a look at. We're looking at the 2022 step 3 paper, and it's question number 11 that we're going to be taking a look at, which is from section C, the statistics and probability section of the paper. Okay, so just a word of warning, this is going to be a very difficult video for me to make, and it might be a very difficult video for you to watch from time to time. For the simple reason that there's going to be a lot of algebraic manipulation involved in this calculation and the solutions of this problem. I make no apologies for the amount of algebraic manipulation that you're going to see in this video. I would strongly recommend that you be prepared to take notes, that you are prepared to re-watch certain parts of the video, pause the video if you need to, and so on, okay? Because there is a lot of algebra involved, and it's just the way that it is. It's very typical with step problems to have to do quite a lot of algebraic manipulation. What I would strongly recommend, based on my experience of this, if you are preparing for a step exam, make sure that you've got some stamina when it comes to dealing with algebraic expressions, okay? Make sure you have done some fairly lengthy calculations before you get anywhere near the time of your exam, so that you're building up that mental stamina that you need to deal with fairly lengthy algebraic expressions, and sometimes quite intricate algebraic manipulation. Okay, so let's have a look at the problem then. So question number 11, a fair coin is tossed n times and the random variable x records the number of heads. The mean deviation delta of x is defined by delta equals the expectation of the modulus of x minus mu, where mu is the mean of x. So hopefully, if I remember, then I will put the question up on the screen somewhere at the bottom. I don't know which side yet, but I'll also leave a link in the description to this video to the past paper so you can download it yourself. You can have a go at this problem and the other problems as well. Because it is step 3, then it is going to touch on some material that typically you will only come across if you're doing the A-level further maths course. I can't imagine that there are going to be many people that are doing normal maths that end up doing a step 3 paper, but if you are doing normal maths and you're not doing further maths at A-level, and you're preparing for a step exam and you're using step 3 as kind of extra preparation, that's good. I encourage that, but be prepared for a bit of independent work involved. You're going to have to teach yourself a few techniques, a bit of theory that's not included on the normal A-level maths course that you're typically only going to come across on the further maths course. But I do recommend that, by the way, if you are preparing for a step exam, to be prepared, whether you're doing normal maths or further maths or whatever, to be prepared to go beyond your particular specification and learn about mathematics in a wider context. So we've got n, uppercase N, a fair coin is tossed n times, uppercase N, and the random variable x records the number of heads. This is a textbook binomial distribution, right? X is a binomial distribution. It's got a fixed number of trials, 2 possible outcomes, heads and tails, the same probability of success at each stage, so on and so forth. X follows a binomial distribution with parameters n and half. Okay, we're told that delta is equal to the expectation of the modulus of x minus mu, where mu is the mean of x. In other words, mu is equal to the expectation of x, which, as you probably know, in this case, because x follows a binomial distribution, its mean is just the product of its parameters. So I'm not going to go into the details about why that is and so on and so forth. We're going to take that as given here. Something else that's going to be quite useful to us to know is what we mean by the expectation of a random variable, how we calculate that. So if y is a discrete random variable, then the expectation of y is equal to the sum over y, the possible outcomes, of y times the probability that y is equal to y. Okay? And also, because we're dealing with a binomial distribution, something that people really muck up with sometimes is that they understand this as they equate this not only with the number of trials of the random variable, but also the number of possible outcomes. It's not. If we've got n trials, we've got n plus 1 possible outcomes. Okay, you flip a coin 4 times, and you record the number of heads, the total number of heads that you obtain in those 4 flips. Well, you could get 0, 1, 2, 3, or 4 heads, 5 outcomes. Okay, same if you flip the coin 20 times, right? You've got all of the numbers from 0 to 20 as possible outcomes. Well, that's 21 outcomes. Okay, that's going to be significant to us. It's little observations like this that seem trivial. It's actually going to be quite significant to us at various stages throughout our calculation. Okay, so let's have a look at the first part of this. So in the case when n is equal to 2 times lowercase n, in other words, we've got an even number of trials, show that the probability that x is less than or equal to n minus 1 is equal to half 1 minus the probability that x is equal to n. Okay, so just to be clear, x is distributed binomially with parameters 2n and a half, and therefore the expectation of x, which equals mu, is equal to n. Okay, it's worth just jotting things like this down from time to time, because rather than trying to keep everything in your head, this information may or may not be useful, but if it's there on the page, you don't have to worry about forgetting it. Okay, right, so what are the possible outcomes here? 0, 1, 2, n minus 1, n plus 1, 2n minus 1, 2n. So these are all of the possible outcomes. That's, again, seemingly minor observation, but it's going to be critical for us when it comes to doing our various calculations. So, something that's going to be really useful for us to notice as well is, because of the particular binomial distribution that we're dealing with, where the probability of success is equal to a half, this is a symmetrical distribution. Okay, symmetrical binomial distribution. Symmetrical in this sense, that the probability that x equals 0 is equal to the probability that x is equal to 2n. The probability that x equals 1 equals the probability that x is equal to 2n minus 1. And in general, the probability that x is equal to r, where r is, and I'm just going to restrict, I don't really need to do this, but I am going to anyway. R is less than or equal to n minus 1 is an integer, is equal to the probability that x is equal to 2n minus r. So in other words, the probability of this outcome is equal to the probability of this outcome. The probability of this outcome is equal to the probability of this outcome. The probability of that outcome is equal to the probability of that outcome. Okay, and then we've got this odd one out, biggie in the middle. Okay, so this comes about by the symmetry exhibited by the binomial coefficients, for example. So if we've got m choose k, this is equal to m choose m minus k. Okay, it's this that really allows me to say, to assert each of these equalities. So what I can do then is I can group all of these outcomes together into an event. Okay, the event that x is less than or equal to n minus 1. I've got this event, which is x equals n, and then I can group all of these together into the event x is greater than or equal to n plus 1. So these are all of the possible outcomes, and therefore the probability of me obtaining one of these outcomes, that's not gone far enough, has it? Obtaining one of these outcomes is equal to 1. It's certain. I must obtain one of these outcomes. There are no other hidden outcomes or whatever. But because they're mutually exclusive events, their total probability is equal to the sum of their individual probabilities. So that means that the sum of their individual probabilities must be equal to 1. Now, because of this symmetry, the probability of this event is equal to the probability of this event. So twice the probability that x is less than or equal to n minus 1 plus the probability that x equals n is equal to 1. And as you can see, it's just a bit of a algebraic fiddle to show that you've got probability that x is less than or equal to n minus 1 is a half 1 minus the probability that x equals n. And we're done, right? Job done. So a nice easy problem, as long as you can spot and as long as you're aware of the various properties of the distributions and so on and so forth. Okay, easy peasy. So let's move on to the next part of the problem. Get rid of this, we don't really need it anymore. We are going to be using this result, but we're not going to need it for a while at least, so let's just get rid of it. So what we need to show now is that delta is equal to, what is it? The sum from r equals 0 to n minus 1 of n minus r times 2n choose r times 1 over 2 to the power of 2n minus 1. Okay, this is what we need to show. What's our start point though? Our start point is this, okay? Delta is equal to the expectation of x minus, a modulus of x minus mu. Well, that's going to be the sum from r equals 0 to 2n of the modulus of r minus, remember mu is equal to n in this case, 2n choose r times 1/2 to the power of r times 1/2 to the power of 2n minus r, okay? So it's worth noting that for r less than or equal to n, modulus of r minus n is equal to n minus r. And for r greater than or equal to n plus 1, and we're talking about r being an integer here, modulus of r minus n is equal to r minus n. Okay? So this I can split into the following. The sum from r equals 0 to n of modulus of r minus n, which is going to be n minus r, 2n choose r, and I can combine that into 1/2 to the power of 2n, plus the sum from r equals n plus 1 to 2n of r minus n, 2n choose r, 1/2 to the power of 2n. Okay, so what next? Right. What I want to show, there is a further simplification that I can make as well. In the case when r is actually equal to n, that knocks out one of these terms here. Okay, so actually I don't need to sum from r equals 0 to n, I can sum from r equals 0 to n minus 1. That's going to be quite crucial because I've got the same number of outcomes here, effectively in this sum, as in this sum. I've got n outcomes here and n outcomes here. Okay, that one in the middle, when r is equal to n, I can effectively knock it out. It's still there, it's still an outcome, it's just it doesn't contribute to the expectation. Okay. Also, something else that might explain a little bit more clearly what some of the manipulations that I'm going to do. If we think about the graph of modulus of, let's go for modulus of x minus n. Okay, what will this look like? Well, if we've got n here, it's going to look like this. Okay, it's going to look something like that. So the equation of this line here, this bit of the function, is going to be y equals n minus x, and this is going to be y equals x minus n. Importantly, the value at n minus 1 is going to be equal to the value at n plus 1. n minus 2, the value is going to be equal to the value at n plus 2. Okay, and so on and so forth. So n minus r is going to have the same value as n plus r. So this is going to be kind of important, because I'm going to be kind of matching things up from here to here. So let's have a look. So when r is equal to 0, for example, 0, 1, 2, 3, up to n minus 2, n minus 1, the values of n minus r are going to be n minus 1, n minus 2, this is going to be 2 and 1. But then if I consider r equals n plus 1, n plus 2, up to 2n minus 1 to n, the value of r minus n is equal to 1, 2, up to, that's going to be n minus 1, that's going to be n. So this is one symmetry, and that's what I'm kind of illustrating here with this diagram. I'm illustrating it here just as an array of numbers, I guess. What I'm showing is that for every value that I obtain here, for the different values of r, there's a corresponding value over here as well. Okay, so when r equals 0, I get the same value here with n minus r as I do over here when r is equal to 2n. When n is equal to n minus 2 here, I get the same value of n minus r as when r is equal to n plus 2 over here. And another symmetry that I can take advantage of is symmetry with the binomial coefficients. So again, when r is equal to 0, let me just write it out again. So notice that the symmetry kind of works inwards. So if I've got all of the outcomes listed from 0 to 2n, the symmetry 0 corresponds to 2n, 1 corresponds to 2n minus 1, 2 corresponds to n minus 2, and you gradually work in until you get to n minus 1 and n plus 1, and then you've got n just stuck in the middle. So what about binomial coefficients? Well, here I'm going to get r equals 0, 2n choose 0, 2n choose 1, 2n choose 2, and here I'm going to get 2n choose 2n, 2n choose 2n minus 1, but this is equal to this, this is equal to this, this is equal to the next one down. This will be, the binomial coefficient corresponding to this value of r is the same as this one, and this one. So again, I get this pairing. If I've got all of the outcomes listed from 0 to 2n, 0, 2n can be matched up. Not only in terms of the n minus r and r minus n matching up, but also the binomial coefficient. The next one's in on each side correspond. The next one's in, the next one's in. Okay, so with that in mind, what that means is that this sum is going to be equal to, in value, to this to this sum here. So one thing that you would have to do here is actually figure out how you're going to communicate this idea. So I'm doing it in words through the video. I'm not necessarily writing it all on the board. I'm just giving you an idea about what's involved in the solution to this problem. You, in the exam, obviously would need to find a suitable way to write this down to make your idea clear. It doesn't need to be perfect. Don't expect perfection with your solutions. You just have to be able to communicate clearly your ideas. Even if they're slightly imperfectly communicated, that doesn't matter. As long as you've got a clear indication of what your idea is and where your ideas are coming from, that's the main thing. So what I can say then is that, eventually conclude, is that this and this are equal in value. So this is just this sum is equal to twice the sum from r equals 0 to n minus 1 of n minus r, 2n choose r, half to the power of 2n. This can, okay, so 2 times half to the power of 2n is 2 over 2 to the power of 2n, which is, of course, 1 over 2 to the power of 2n minus 1. So this is equal to the sum of n minus r from r equals 0 to n minus 1, 2n choose r, times 1 over 2 to the power of 2n minus 1. Okay, so far so good. On to the next part then. The next part, part C, there's two parts to part C. The first part's relatively straightforward. It's just a fairly simple kind of manipulation of binomial coefficients. Okay, let's have a look. So what we need to prove is that for r greater than 0, important, r, 2n choose r is equal to 2n minus 1, r minus 1. Okay. So one thing that I know is a problem with a lot of A-level students, A-level math students, is that they don't know how binomial coefficients can be defined in terms of factorials. Excuse me. To a lot of A-level math students, binomial coefficients are effectively just something that just pop out of their calculator. Okay. So okay, maybe when you're doing normal maths, then it's not quite so important for you to know how binomial coefficients are defined in terms of factorial. I still think it is important, and I always encourage my students to learn this, even though most of the time they don't. But if you're doing further maths, and definitely if you're preparing for a STEP paper or a mathematics admissions test, please make sure that you know how to define, how to express binomial coefficients in terms of factorials, and that you're familiar with manipulation of factorial expressions. Okay, just takes a bit of practice. You've got to will yourself to do it, rather than just relying on your calculator all the time to just give you the answer. So what we've got here is that r, 2n choose r is equal to r times 2n factorial over r factorial times 2n minus r factorial. Okay, so the factor of r here cancels with the factor of r in the factorial here, giving 2n factorial over r minus 1 factorial, 2n minus r factorial. Notice that 2n minus r can be written as 2n minus 1 minus r minus 1. So this is equal to 2n times 2n minus 1 over r minus 1 factorial, sorry, 2n minus 1 factorial, r minus 1 factorial times 2n minus 1 minus r minus 1 factorial, which is exactly what we need, 2n minus 1, r minus 1, okay? So I personally didn't really have any difficulty with this because these are fairly standard techniques to use when dealing with manipulation of binomial coefficients. So this was a very natural thing for me to do. However, the next part of the problem caused me some difficulties. Okay, so we've got that result. Notice that r has to be greater than 0. That does play a role in what we're about to do. These little details like this, pay attention to them because sometimes they do have a big impact. So what we need to show now is that delta, so we've shown that, we need to show now that delta is equal to n over 2 to the power of 2n times 2n choose n. Is that right? Yeah. Okay. So this took me several attempts to get, and I'm not gonna lie and try to claim that I saw what to do here straight away, because I didn't. It was just playing around with the expressions until you find something that works. It turns out that what I was doing was kind of the right thing. It's just you've got to see what you need to see, and sometimes you just don't. What I was kind of getting at earlier, all you can do is try to minimize the possibility that you don't see what you need to see. But it can still happen, right? Sometimes it takes just a few minutes. Other times it can take a lot longer. So for me here, it was at least 3 attempts at this problem to get the solution. And even then, I had to kind of rewrite out my solution in a way that was clear, because when you initially write a solution to a problem, it can be a bit all over the place, as you probably well know. What is important is that you make it clear what you want, the story that your solution is meant to tell. What order do things happen in your solution? This is your job to make clear. I know it's a bit of an inconvenience when you're strapped for time. You've written out what is effectively in your head a solution, but it's kind of all over the place. Well, be conscious of the fact that the person reading your work doesn't have access to your thoughts. So what makes perfect sense in your head, and you feel is kind of expressed on the page, may not be clear to somebody that's reading. You have to be conscious of the fact that somebody somewhere is going to have to read your work and understand it. And if they can't understand it, then you can't get credit for it. It's as simple as that. Okay. Now, your examiners will work quite hard to give you marks. You know, they will try to justify. They're usually quite generous. From what I understand, they're usually quite generous. But there is a limit to that. So if your solution's all over the place and it's literally incomprehensible to somebody that's reading it, you can't expect to get marks. In the same way that if you were writing a novel, you couldn't expect somebody to understand what story you were trying to tell if you were just writing random sentences, right? If the sentences were supposed to be read in a particular order, but they were kind of scattered randomly throughout the book, you might know which order, but nobody else does. Okay, so you've got to make sure that you're expressing your ideas clearly enough for somebody to understand. If you don't, unlucky. Right, so our starting point here is going to be this. Okay, so it's going to be, this is equal to the sum from r equals 0 to n minus 1. Now what I can do is I can split this up into n times 2n choose r times 1 over 2 to the power of 2n. And I'm going to write it as 1 over 2 to the power of 2n times 2, and I'm going to write the 2 here just to save a bit of space. Minus the sum from r equals 0 to n minus 1 of r 2n choose r 1 over 2 to the power of 2n minus 1. Okay, I've done this deliberately. Hopefully we'll see shortly why. Okay, so this is one other thing that I can do here is I can take the 2n out of this sum, right? Because this is a fixed quantity. It's a constant. Constants can be pulled out of sums. So let's do that. So I get 2n times the sum of this thing here, okay, minus the sum of all of this. Right, so I'm going to have to do a couple of things now. I'm going to have to deal with this, and I'm going to have to deal with this, and I'm going to have to deal with them really separately. Okay, so, and this is going to take up a bit of space. So this here, when I say this, I'm just talking about the sum. This is equal to the probability that x is less than or equal to n minus 1. This was one of the things that I initially overlooked. When I first went through this, I didn't spot this. Okay, it seems obvious to me now. That's just, but again, that's how it is. That's how it works. Sometimes you miss the obvious. But we already have a formula for that. It's equal to what? It's half 1 minus the probability that x is equal to n. Which is equal to half minus a half times probability that x is equal to n. Remember, x is distributed binomially with parameters 2n and half. That's going to be 2n choose n times half to the power of n times a half to the power of n, or half to the power of 2n. Okay? So therefore, this thing here is going to be 2n times that. So let's extend that now. So we've got 2n times, so 2n times this, which is 2n times all of this, which is equal to n minus n times 2n, choose n, times by half, or 1 over 2 to the power of 2n. So this is looking good, right? It's looking good. We're not there yet. Sorry, is that right? Yeah, that's right. We're not there yet, but it's kind of we're on the right lines, evidently. What about this thing over here? So the sum from r equals 0 to n minus 1 of r, 2n choose r, 1 over 2. In fact, I'll leave that off. No, I will include it. Undecided. There we go. So this is equal to, right, okay, when r is equal to 0, this, the term corresponding to r equals 0 is just 0. So I can, rather than summing from r equals 0, I can sum from r equals 1. And remember when we proved that r times 2n choose r is equal to 2n times 2n minus 1 choose r minus 1. What was the condition? R is greater than 0. Now I can apply that to all of the terms here. So this is going to be equal to the sum from r equals 1 to n minus 1 of 2n times 2n minus 1, r minus 1, 1 over 2 to the power of 2n minus. In fact, I'm going to write it as a half. So it'll make it a little bit clearer what I'm about to do. This 2n, again, is a constant. It can come out of the sum. Now, what is this thing? Again, I missed this the first time round. If we've got y is distributed binomially with parameters 2n minus 1 and a half, this is the probability that y is less than or equal to n minus 2. Yes, n minus 2. Why n minus 2? Because notice that here we've got r minus 1. So when r is equal to 1, we get 2n minus 1 choose 0. Next, 2n minus 1 choose 1. Up to 2n minus 1 choose n minus 1 minus 1, n minus 2. What are the possible outcomes here? That is 0, 1, 2, n minus 1, n plus 1, up to 2n minus 1. How many outcomes are there altogether? There's 2n, right? Remember, there's always one more than this parameter, 2n. So that means that because of the symmetry of the distribution, the probability of this event, the probability that y is less than or equal to n minus 1, is equal to half, which is equal to the probability that y is greater than or equal to n. Okay? Just using the properties of the distribution. So therefore, this is going to be equal to 2n times a half minus the probability that y is equal to n minus 1. Okay? Which is equal to it's going to be equal to n minus 2n times 2n minus 1, choose n minus 1, times half to the power of 2n minus 1. Okay, good stuff. But what about this thing now? So for once I'd got to this point, things were starting to kind of right themselves. Okay, which is very often the case. Once you get that right way of thinking about something, things just flow out quite naturally. When you're trying to solve a challenging problem, non-routine, difficult, challenging problem, much of the difficulty really is actually coming to a thorough enough understanding, a clear enough understanding of the problem that you're dealing with, and viewing it from the right perspective. That's, in my opinion, 95% of the work. Once you've got that, then everything's straightforward, and you can look back over what you've done and you can think, why did it take me so long to get that solution? And the answer to that is, it just did. It just did. You've just got to hang around long enough. You've got to give yourself enough time to see things in the way that you need to see them, that you personally need to see them for that light bulb moment to happen. You know, and the light just clicks on. Right, so let's have a look at this thing then. So 2n, so this is a separate calculation here, 2n, 2n minus 1, choose n minus 1. Again, it's just fiddling around with the binomial coefficients here. So what we get here is that we get 2n times 2n minus 1 factorial over n minus 1 factorial times, what's it going to be, 2n minus 1, what's that going to be, 2n minus 1 minus n minus 1 is 2n minus n plus 1, cancel, it's just going to be n. Oh, that would much, yeah. Okay, n factorial. So here's a little bit of a trick that might be useful, is I'm going to multiply numerator and denominator of this by n. How did I know to do this? It's just, again, seeing things in the right way, and being on some level conscious of the kinds of things that you have done in the past. This is why it's so important to get lots and lots and lots of experience of solving problems before you get to your exam, because you need to have in the back of your mind a kind of reference. I'm not saying that you should try to memorize everything that you do, but in the back of your mind, these techniques that you've come across before, that you've used, will get kind of stored in a certain way. And you'll be surprised at when your brain can suggest to you which techniques to use. It's a certain intuition that you develop. And obviously people are professional mathematicians in research and things like that, you know, way above what I do. They'll be much better at stuff like this than I am. But still, it's the same principle, okay? You're developing an intuition for the kinds of techniques that you've seen used, that you have used yourself, and also it makes you more open to new possibilities, okay, making new connections between things. Okay, so I'm going to write this as n times 2n over n times 2n minus 1 factorial over n minus 1 factorial n factorial, which is equal to n times the 2n can be absorbed into this to make 2n factorial over, and the n can go into this n minus 1 factorial to make n factorial. Ah, nice one. That's n times 2n choose n. So this is equal to n minus n times 2n choose n, a half to the power of 2n minus 1. Right, now we're cooking, right? Now we're on a roll. Get rid of all of that. So therefore, this is going to be equal to this take away this. So it's going to be n minus n times this thing. Importantly, this n is going to cancel with this n here. So what I'm going to end up with is minus n choose 2n choose n, 1 over 2 to the power of 2n, plus, because it's minus this thing, so it's going to be minus n plus this, 2n choose n, 1 over 2 to the power of 2n minus 1, and I'm going to write it as 2n times 2n choose n, 1 over 2 to the power of n. Why? Because then I've got minus, notice the similarity here, this is effectively something of the form minus x plus 2x, which is just x, obviously. So it's going to be n over 2 to the power of 2n, 2n, choose n. Bingo, we're there. Okay, that's exactly what I needed. So that took me a few attempts to get that. Okay, hopefully this all makes sense. Right, we're on to the final part now. And effectively what we're going to be doing is what we've just done through all of the previous parts all over again. But now we're doing it from scratch, all on our own. Very typical of a step problem where you're kind of you're kind of guided to a certain extent through something, although with much less guidance than you would typically expect on a normal A-level maths exam. But then right at the end, you just dropped in it. You're on your own. Okay, so let's have a look at this last part. Okay, so the last part of this is find a similar expression for delta in the case when uppercase n equals 2 times lowercase n plus 1. Okay, so have you had enough yet? Okay, so now we've got n is equal to 2n plus 1, so x is distributed binomially with parameters 2n plus 1 and half. Therefore, expectation of x equals mu, which is going to be equal to, in this case, 2n plus 1 over 2, or, if you prefer, n plus a half. Okay? So I'm writing these up here because we kind of found these things useful in the previous case. So I'm expecting that they're going to be useful here. So what we're aiming for an expression for delta, which is the expectation of modulus of x minus mu, which in this case is going to be the expectation of modulus of x minus n plus a half. So this is equal to the sum from r equals 0 to 2n plus 1 of the modulus of r minus n plus a half. Probability, so it's going to be 2n plus 1, choose r, half to the power of r, half to the power of 2n plus 1 minus r, which of course is equal to the sum from r equals 0 to 2n plus 1, r minus n plus a half, modulus 2n plus 1, choose r, half to the power of 2n plus 1. It's going to be in many ways very similar to what we've already done. Kind of split this up. Now, importantly, we've got an even number of possible outcomes here. 0, 1, 2, up to 2n plus 1. We've got 2n plus 2 outcomes. This is equal to the sum from r equals 0 to, let me think how's going to be a good way to split this up. Well, when n is less than or equal to, when r is less than or equal to n minus n plus a half, then modulus of r minus n plus a half is going to be equal to n plus a half minus r. Okay, so we get n plus a half minus r from r equals 0 to n of 2n plus 1 choose r, a half to the power of 2n plus 1. What about when r is greater than or equal to n plus 1? In that case, we get modulus of r minus n plus a half is just equal to r minus n plus a half. Plus the sum r equals n plus 1 to 2n plus 1 of r minus n plus a half, 2n plus 1 choose r, half to the power of 2n plus 1. What I claim is that these are going to be equal in value. Okay, whereas before in the previous case I was able to kind of eliminate one of the terms of the sum. I don't need to do that here, okay, because none of these terms are necessarily going to be equal to 0. But that's fine because I've got an equal number of terms here and an equal number of terms here. And it all comes down again to exploiting those symmetries between these and these. Okay, so again, when r equals 0, 1, 2, 3, up to, n minus 1 and n, we get n plus a half minus r is going to be equal to n plus a half, n minus a half, n minus 3 halves, down to, that's just going to be a half, isn't it? And then we're going to get 3 halves. And when r is equal to n plus 1, n plus 2, 2n, 2n plus 1, we get r minus n plus a half. It just goes in the other direction, right? So n plus 1 minus, brackets around that, is going to be a half. It's going to be 3 halves. We're going to get n minus a half, n plus a half. So there's a symmetry between the values of this and the values of this. Again, it's r equals 0 corresponds to 2n plus 1. R equals 1 corresponds to 2n. 2 corresponds to the next one. n minus 1 corresponds to n plus 2. n corresponds to n plus 1. But the same also with the binomial coefficients. Okay, so the binomial coefficient 2n plus 1 choose 0 will be equal to the binomial coefficient 2n plus 1 choose 2n plus 1. 2n plus 1 choose 1 will be the same as 2n plus 1 choose 2n. All the way down to 2n plus 1 choose n will be the same as 2n plus 1 choose n plus 1. Okay, it's just a well-known property of binomial coefficients that they are symmetrical in this way, kind of working inwards from the outside. Okay, so the conclusion is, and again, you will have to find a way, as I would if I was doing the exam, have to find a way to clearly communicate that idea. Okay, there's not necessarily just one way that you can express it. There's all sorts of ways, but you just have to make sure that you clearly communicate it. So what we get is that this is equal to twice the sum from r equals 0 to n of n plus a half minus r. 2n plus 1 choose r, half to the power of 2n plus 1. Okay, so this is kind of the analogous result to part B, part 1b that we had previously. But we now need to continue with this, okay? So let's do that. I'm going to make a note of this because I need to clear some space, but I want to make a note of that. So, oh, sorry, I could actually just tidy this up a little bit. So I get delta equals the sum from r equals 0 to n of n plus a half minus r, 2n plus 1, choose r, and then here I'm going to get a half, so it would be 1 over 2 to the power of 2n plus 1 times 2, which is just going to be times 1 over 2 to the power of 2n, okay? Just to bring it more in line with the form that we got in part BI. Okay, so let's have a look at the next part. So our start point is going to be roughly the same as kind of what we had before now with the previous case when we dealt with an even value for uppercase n. So we can write delta, we can split this up in other words. So we can write it as the sum of n plus a half to n plus 1, choose r, from r equals 0 to n, of, I'm going to write it as a half to the power of 2n, minus the sum from r equals 0 to n of r times 2n plus 1, choose r, half to the power of 2n. So I can bring this out of the sum because it's just a constant. And I'm wanting to use a similar technique as to what I used before, recognizing that this has a certain binomial probability. So to do that, it's going to help if I put a 2 here and add a power to the half here. Okay, so I recognize this then as the probability that x is less than or equal to n. So let's have a look at the possible outcomes of x. There's 2n plus 2 possible outcomes. There's these, and they're symmetrical. The probabilities are symmetrical. So I can group these n plus 1 events together, or outcomes together to create an event, and these n plus 1 outcomes together to create another event. But because of the symmetry, the probability of this, which is the probability that x is less than or equal to n, must be equal to a half. Perfect, right? And this must also be equal to a half, but that's kind of beside the point. So therefore, this is just equal to 2n plus a half times a half, which is just equal to n plus a half. So far, so good. So what about this thing over here? So let's have a look. So we've got the sum, again, when r is equal to 0, I can knock out one of the terms here. So I actually need to sum from 1. So it's a sum from r equals 1 to n of, in this case, it's going to be 2n plus 1, and then 2n r minus 1, half to the power of 2n. The 2n plus 1 can come out of the sum. It's a constant. And then if I think about the random variable y, which now has a binomial distribution with 2n and a half as its parameters, then this is the probability that y is less than or equal to n minus 1. Yes, n minus 1, even though the sum is up to n, because we've got r minus 1 here. So I kind of explained this earlier. The binomial coefficients will be 2n choose 0, 2n choose 1, up to 2n choose n minus 1. Okay, so, but hang on a second. Haven't we already dealt with this case? Right at the very start. This is going to be equal to what? Half 1 minus the probability that y is equal to n. Well, that's going to save a lot of time potentially. So that's going to be equal to half minus a half times 2n choose n times 1 over 2 half to the power of 2n. So this is looking good, right? So it's just this, take away this now. And then I've got a little bit more manipulation to go. But once I've done that, we're all good. So let's have a look. So delta, therefore, is going to be equal to n plus a half minus 2n plus 1. In fact, I'm going to write it as 2n plus 1 over 2 times 1 minus 2n choose n half to the power of 2n, which equals n plus a half minus 2n plus 1 over 2 is n plus a half, so it's going to be minus n plus a half. That's a good sign. Plus minus minus plus n plus a half times 2n choose n a half to the power of 2n. Okay, so we're not quite done yet, but we're certainly getting there. Because I could write this now as n plus a half over 2 to the power of 2n. It doesn't quite fit the form that I had previously. Okay, so when I had, for example, n equals 2n, we got that delta is equal to, what was it, n over 2 to the power of 2n, 2n choose n. This doesn't, it just doesn't fit that form over here. Because I want this number here to match this number here. I want this number here to match this number here. That's not what I'm getting here. So I've got to work a little bit to try to correct that. Okay, so how can I do that? Well, let's do this. Let's just come up here to do it as a separate calculation. So n plus a half over 2 to the power of 2n, 2n choose n, is going to be equal to, so multiply numerator and denominator by 2, I get 2n plus 1 over 2 to the power of 2n plus 1, 2n choose n. Okay, so let me just have a look. Okay, so this equals 1 over 2 to the power of 2n plus 1 times 2n plus 1 times 2n factorial over n factorial times n factorial. Which is 2n plus 1 factorial over n factorial times n factorial, but that's not really what I want, because I want this to become a binomial coefficient. So I really want n plus 1 factorial in here, so that it's 2n plus 1 minus, because 2n plus 1 minus n is equal to n plus 1. So I can force an n plus 1 in here by multiplying numerator and denominator of this by n plus 1. Okay, so maybe I'll just take it step by step so you can see a bit more clearly what I'm doing. So I'm going from this to 1 over 2 2n plus 1 times n plus 1 times 2n plus 1 over n plus 1. It's very similar to what I did in the previous case, times 2n factorial over n factorial times n factorial, which is 1 over 2 to the power of 2n plus 1. In fact, I'll write it as n plus 1, times 2n plus 1 times 2n factorial gives 2n plus 1 factorial. Leave that n factorial as it is. N plus 1 times n factorial gives n plus 1 factorial. So therefore I get n plus 1 over 2 to the power of 2n plus 1 times 2n plus 1, choose n. And that's it. Delta is equal to this in this case. And that fits much more closely with the value of delta that I got in the previous case. So I'm satisfied with that. I'm happy with that. I'm not happy with this. I don't think this is what is really being aimed for. There's kind of nothing wrong with it, I suppose. It's just, it doesn't quite fit the bill, in my opinion. This does much more closely. I don't know, in the exam, if you presented that, or even if you presented it as 2n plus 1 over 2 to the power of 2n plus 1, 2n choose n, would you get your marks? I honestly don't know. I don't. You would get plenty of credit, but I don't think that this is quite what is desired. Again, it doesn't quite fit the form that we had previously, which leads me to believe that probably this would be where you would get your credit for doing this. Okay, so we're finished. Have you made it this far? So as you can see, there's plenty of algebra involved in that. It's been a very difficult video for me to make. This is actually my third attempt at making this. Very difficult to keep up with all of the algebra, trying to do it off the top of my head and things like that. So congratulations if you've made it this far. Please show your support for this channel if you're finding it useful by hitting the subscribe button and giving this video a like. I don't get paid for making these videos. I don't make a single penny. I make these videos because I enjoy making them. I enjoy the challenge of making them, and I enjoy helping you to prepare for your exams and to reach your true potential. So if you are finding these videos useful and you want me to keep making these videos, I can only do that whilever there's some support for me to do it. So if you wouldn't mind just hitting the subscribe button and letting anybody else that you think might benefit from these videos, letting them know about these videos so that they can also learn from them and also show their support. So that brings us to the end of this problem, and it brings us to the end of this video. So thank you very much for watching right to the end if you've managed it.